In this webinar, we're going to take a look at the tools in Maple for working with LeastSquares fits in Maple. Now, there are 4 packages that contain 13 Maple commands that are relevant for LeastSquares calculations. There's a CurveFitting package that has a LeastSquares command. And I've highlighted in red the essential ideas here. This command deals with univariate models, function of one variable, and the model is linear in the parameters. What you get back is a general solution for an underdetermined problem, but you cannot get a minimum norm solution. In the linear algebra package, there is also a LeastSquares command that applies to univariate model that's linear in the parameters, and you can get back a general or a minimum norm LeastSquares solution to the problem of the form ax equals b. And here the input can be a set of equations, one of the few places where you can actually input a set of equations. There's also a LinearSolve command, and you will get back a general or a minimum norm solution to an underdetermined problem, but the problem has to have consistent linear equations that are given in a matrix vector format, and the command will fail for an overdetermined system. So you see these subtle differences between the behavior of the commands. In the optimization package, there are 3 commands that are relevant. NLPSolve, Nonlinear Program Solve. Well, this would obtain a local minimum of a sum of squares of deviations. Minimize command. Again, you would input the sum of squares, and this command supports various constraints. There is a LeastSquares LSSolve command which will obtain a local minimum of 1/2 the sum of squares. Now the GK could be one of these differences, or it could be more general. So you would input this list of residuals or a matrix vector format, and it also supports various types of bounds and constraints. And finally, in the statistics package, there are some 7 commands that are relevant. There is a fit command. There is a LinearFit and a Nonlinear Fit is a traffic cop. It passes off problems either to LinearFit or NonlinearFit. So if the model is linear, it will go to LinearFit. If the model is nonlinear, it will go to NonlinearFit. In LinearFit, the model has to be linear, and it passes the problem off to numerical linear algebra. NonlinearFit will solve nonlinear models, and it will pass that off to the LSSolve command and optimization. Then there are these 4 special fitting commands: PolynomialFit, ExponentialFit, LogarithmicFit, PowerFit. PolynomialFit is your standard polynomial fit. Exponential, logarithmic, and power, they linearize and then send it off to the linear solver, which is numerical linear algebra. And I will have something to say about this process of linearization of what's essentially a nonlinear model. Now, all 7 of these commands in statistics work in floating point arithmetic only. You can't get any exact solutions like you can from some of the other packages. And you can get individual items as a result, or you can get back a module containing all relevant regression analysis details that you see here in this table. For linear models, you can get any of these items. I think there are 20 altogether. But for nonlinear models, you get only these on the left. So, as I was going through this material, I needed to have in my head a model of the universe of discourse that we were going to talk about here today. And I think in terms of equations. And as you think about equations, you got to realize, well, you might have a system where you have redundant equations, that the equations haven't been boiled down to the least possible number. So in my thinking here, I've mentally removed redundant equations. And then I've said I could have 5 equations in 4 unknowns. So I have more data than parameters. And these would necessarily be inconsistent. And that's the least squares problem. If you had 5 equations and 5 unknowns, and remember, we've removed redundant equations. 5 equations and 5 unknowns. These equations could be consistent, or they could be inconsistent. The consistent case, I call it interpolation. You're just solving equations. If the equations are inconsistent, then you have to do least squares. And if you had 5 equations and 6 unknowns, you don't have enough data points, you can again have consistent equations or inconsistent equations. And both of them would require a least squares solution. And so this is how I structured my set of examples to cover these cases. So what collection of examples did I come up with to explore these different possibilities? So I broke it down this way. You can have univariate problems and you can have multivariate problems. You could have a case where you have too many equations, a case where you have too few equations. In both instances, too many, too few. So if you have too many equations, they could be linear, they could be nonlinear. They could be linear, they could be nonlinear. Linear, nonlinear, linear, nonlinear. If you have too many equations, they will necessarily be inconsistent. Too many equations, necessarily inconsistent. Too few equations, they could be consistent or inconsistent. Same here for both linear and nonlinear cases. Multivariate situation. You have too many equations, they could be linear, nonlinear. Too many equations are necessarily going to be inconsistent. If you have too few equations, they could be consistent or inconsistent. I've chosen to consider just the inconsistent case, down here consistent or inconsistent. So this is how I structured my collection of examples, and I will do almost all of these in our discussion. So let's start with example 1. Okay, this is univariate, linear, too many equations, necessarily inconsistent. So here is my fitting function. It's a linear function, it's a constant, and then multiples of sine kx. What are my data points? I took 10 data points. And I took them along y equals x squared, equally spaced, and I went an x from 0 to 3. Let's initialize. And I've got this stuff typed out ahead of time so that you're not watching me type. I will explain these things as I go. So here's the fitting function. Sine function. I'm using syntax-free techniques where possible. And you'll notice I use this assign function option to take care of defining the function. Okay, then I needed a sequence of x values, so I took 3k over 10, where k goes from 1 to 10. So the first x value is 3/10. And then I took the corresponding y values as x squared. So how would the curve fitting package tools or tool work? Well, it has a LeastSquares command, so curve fitting LeastSquares, x values, y values, independent variable, and the fitting function. And the return is this fitting function. Now I drew a graph here where in black is y equals x squared. These are the data points that are picked along that curve. And this is the fitting function in red. Just want to see how good a job this fitting function would do with that data. Now, there is a curve fitting assistant which has been moved to the tutors, I believe. And it's tucked here under optimization. If you would select optimization here, the assistant will launch. It can also be launched from the context panel. You need the data, and then in curve fitting, you see this interactive curve fitting. That would also launch the same tutor. So data, launch this assistant. We are doing least squares. Enter f of x because f, the fitting function, has been defined. Maple draws a graph of the fitting function when you click plot, and the data points, and it writes the fitting function here, which you can have returned when you click done. I typically return the interpolant because I can use that to draw the graph. Now, what would the linear algebra package have to say about this particular problem? So, linear algebra has a LeastSquares command. And it's the one place where you can provide equations. So what are the equations? So I'm going to apply the function f to each data point, and this tilde is the item by item application of f to each member of the list x. These are the y values, and the equate command puts an equal sign between the left side and the right side. And so this sets up the set of equations. This is a set of the parameter names, b0 through b5. The return is a set of equations giving the values of each of these parameters. Now let's put the problem in a matrix vector format. So let's put it in the form of AU equals V. How would we do that? Well, we'll use in linear algebra the generate matrix command. So again, I'm making a set of equations. It's the same idea here to make a set of equations. And here are the unknown, the parameters. And the return will be the matrix and the vector, A and V. And then I can use the linear algebra LeastSquares command, and the arguments are A and V. The return is now a vector of parameter values, just the values. So here, up here you had equations, B0 equals, B1 equals, and here you just get the parameter values. What would the optimization package have to say about this problem? Let's try the LSSolve, or I think of it as LeastSquares solve, in which case the input is a list VA. And just go back over here for a second. Over here, we input A comma V as a sequence. Over here, it's V comma A in a list. And what is returned is the value for the sum of squares and then a vector of parameter values. So that vector is the same as we found in linear algebra. You could also supply a list of residuals. So here is the difference between the left and right sides, in which case you get back, again, the value of the sum of squares, and now you get a list of equations. Instead of a vector of values, you get equations, B0 equals, and so forth. And finally, let's see what the statistics package has to offer. This is a linear problem, so we could jump right to the LinearFit rather than go through the doorway of fit. We don't need that traffic cop. We can go right to LinearFit. Now, up here, I've raised the info level on statistics to, I think 5 is the highest you can go, which means that if the coders, the programmers, have embedded points in the computation that will return information, then you will get back information by raising info level. And here I set it back down, so for subsequent calculations that we don't muddy up what we're trying to show. List of basis functions, sine kx, and then there was a b0, so we 1. Here is the data, x and y, and the independent variable. So you get back all of this printed information, and the very first thing you see here is SVD tolerance. And I will have to talk about SVD tolerance and its meaning and what it does in a further later example. So for the moment, we're going to pass over that. And you get confidence level, residual sum of squares. You get the model. You get information about the parameters. Okay. You get an r squared value and an adjusted r squared value, and then a repeat of the fitting function. If you issue that same command and included summarize equals embed, then the information that's been displayed up here will be presented in a more tabular form. So here's your fitting function. The fitting function is repeated here. The parameter information is now listed in this table. R squared and adjusted R squared values are here, and information about the residuals presented down here. And here I tried to use the fit command. Now that's the traffic cop. And so first thing it does, it says we're going to send you to LinearFit. And so all of this stuff is going to be the same. And then we'll talk about getting regression analysis. So I used fit here, gave it the data, and asked that the output be the solution module. So all of that regression information is going to be put into this basket, which Maple calls a module, and the name of the basket will be M. And the way you rummage in the basket for results is to write M:\results, and then you put down what you want. Now, there are 20 for this model. There are 20 different things you can ask for. Residual sum of squares, for example. You get the residual sum of squares. Now, if you have been paying strict attention all the way along, now look at this number, 5.22. Back here, in these commands here, from optimization, residual sum of squares, 2.6. And if you remember all the way back, I don't think it's on this screen, there was a 1/2 in front of what you were going to get. So this is actually half the sum of squares. So these are little things that you want to keep in mind so that you don't get totally confused. Here is a way to print each member in that basket one line at a time. Okay, so you applying print to each member. That's what the tilde does. And so you get each piece of information printed out on a separate line. If you didn't do that, if you just printed this stuff out, this would be all big run together in a muddle that's very, very hard to read. Okay, so you got all of this information line by line, or you can ask for specific things by stating, where did it go? By stating here what it is that you want. Okay. One more thing that you can get in the statistics package. There is an error plot command that plots error bars. And so I've just added the graph of y equals x squared and the fitting function, and you have these error bars. And that's one more thing that you can get if you're working in this statistics package. And now in the nonlinear case, we have some examples: a logarithmic fit, PowerFit, ExponentialFit. And here is Michaelis, or Michaelis, depending how you want to pronounce it, Menten, Michaelis Menten, which this function appears a lot in biology. I'm going to do this example rather than this example, any of these examples. So here I'm going to do example 5. And this example, this particular data set came to me when I was at Rose-Hulman. The statistician in the department brought it to me and said, how do we do this in Maple? He had gotten it from the bioengineering people. It comes from some real-life data. It has to do with serum levels in the blood of pigs or something like that. Okay? There were 46 data points. This is a graph of the 46 data points. S is the independent variable. V is the dependent variable. And the data is actually lurking behind this cell. Okay? And I used this example when I wrote my engineering math book. Talked about it in a reporter article, and so on. By way of solution, here's the fitting function. Made it a function. Here's the sum of squares of the deviations. There are two different linearizations that I can come up with for this model. And if we follow through the calculations, we linearize, and then I've used curve fitting, for example, convert that back to the Michaelis-Menten model, and we have this fitting function. Here's a different linearization. Go through the same type of calculations, and we get this version of the fitting function. Now compare them. 1.8, 2.0. 1.4, 1.9. Pretty different. So now let's try to get an exact fit, or the best fit we can, working directly with the nonlinear model. So we have a NonlinearFit command in statistics. We use the NonlinearFit command, and we obtained this fitting function. 1.8 here, 3.4 here. 1.4 here, 8.2 here. And this is half the sum of squares, I believe. No, that is actually the sum of squares. For this one, you would get the actual sum of squares. You can go to the optimization package and use the LSSolve command. And here you get half the sum. See, that 0.8 is half of the 1.6. And the A is the 3.477. The B is 8.22. Consistent there. And we can actually use the normal equations by doing calculus. Take the partial of the sum of squares with respect to A and the partial with respect to B, so that equals 0. Do an F-solve, or numeric solution, and A is 3.477 and B is 8.22 and so forth. So pretty much Maple will solve the nonlinear problem directly. You get the value of the sum of squares for the first linearization, 6.4. For the second linearization, 4.5. For solving the non-linear problem directly, it's 1.6. So that's a much better fit. And if you want to see that graphically, look here. The nonlinear fit is in black. The red and the green are the two linearizations. So bottom line here, as far as I'm concerned, is I am very suspect of linearizations. And I just recently read an article, journal article, where somebody in the medical field that uses this model a lot has realized that maybe with today's set of tools, linearization do fits to this model are not optimal. That one can now solve the problem directly, not the nonlinear version without linearization, and get better results. Now let's try a case where we have too few equations. We'll do a linear model consistent. So we will have more data points than we have equations. I've set that up with complete quadratic, so we have 3 parameters and 2 data points. So that's going to mean 2 equations in 3 unknowns. Work within linear algebra, define the function. Now, when you think about this, you're solving 2 equations in 3 unknowns, not necessarily LeastSquares problem. The equations are consistent, so let's try to solve these 2 equations. F of 1 is 5, F of 2 is 3. There'll be a free parameter, so we can solve for 2 in terms of the third. So I'll solve B and C in terms of A. And that gives me a fitting function that contains a parameter A, unspecified parameter A. And I wanted to look at that family of fitting functions, so I built this little gizmo with a slider controlling the value of a. And you can see how varied the members of this family are. So, although the equations are consistent, if you have too few equations, you have a general solution that has parameters, and the fitting functions can vary greatly. So what does the curve fitting package do for us with this problem? Well, it has a LeastSquares command, and if you give it the data points and the fitting function, you get back the general solution, or the solution containing an arbitrary parameter, and you notice how the parameter is named underscore t, and it'll have a subscript on it, and it agrees with what we had up here. Right, see the 7, etc. What does the linear algebra package provide? Well, there is a LeastSquares command in the linear algebra package, and it will tackle this as a LeastSquares problem. Here are the equations, here are the unknowns, and you have this option to rename the free variable, the free parameter. If we say s, what you get back is a subscripted s, but you don't have that leading underscore, so you don't have to deal with the ugliness of that leading underscore. So the command returns a set of equations defining the parameters, and here I did it. I evaluated the function using that data, and you get the fitting function is a family of fits. But in linear algebra, we can go a little bit further. Let's cast the problem into a matrix vector form, and we'll do that with the generate matrix command. Here are the equations, here are the unknowns. This is the matrix A, this is the vector V, and we are now in the formalism AU equals V. You apply LeastSquares command to that. AV, free parameters will have the name S, and here you have that free parameter, which is really adding to a particular solution an arbitrary member from the null space. If you use the option optimize equals true, you get the minimum norm solution. Now, the minimum norm solution is supposedly the projection of this general solution onto the row space. So Maple's row space command will provide a basis for the row space, but they will be row vectors. We transpose them so that we can make use of the projection matrix command, which requires column vectors. And so we have a matrix that projects onto the row space, and we project the general solution onto the row space, and we get the minimum norm solution. So for these linear models, you can get a minimum norm solution in the linear algebra package. And then this led me to the following question. This green curve is comes from the minimum norm solution. You use the parameter values that you get here in the minimum norm solution. It's one member of this family, one parameter family. And I've always wondered, is there something about this minimum norm solution that's inherent, unique to the physical problem you started with, right? You're trying to fit the quadratic to these two data points. There is a minimum norm solution. What is the relationship between that minimum norm solution and the fitting problem that you're trying to accomplish? I leave that to you all to ponder. And then finally, let's ask, are there any other alternatives? Think about that. The numeric solvers of the optimization package are local. They're not necessarily going to find the minimum norm solution. It could return any member of the general solution. So that's probably not too useful. And the numeric solvers of the statistics package, they don't like underdetermined problems. You can't use that at all. So the options are limited. So now, what happens if you have too few equations and those too few equations are inconsistent? Let's take a look at what those computations will amount to. So I'll use the same fitting function, complete quadratic, and now look at my data points, 1, 5, 1, 3. So you will have inconsistent equations. Well, again, we'll begin with loading the linear algebra package and defining the function f. All right, what does the curve fitting package do for us? Let's apply the LeastSquares command in the curve fitting package. 2 data points, independent variable, fitting function. And now we have a 2-parameter family of fitting functions. T with an underscore, 2 and 3, the 2 different parameters. So I changed that to something simpler, A and B. And so I constructed a graph to explore just how varied the members of this family could be. 2 parameters, moving the parameters around, you can see you can get quite a different set of fitting functions. And finally, let's take a look at what the linear algebra package has to say about this problem. LeastSquares command, I've applied it to a set of equations. F of 1 is 5, f of 1 is 3. 3 parameters. The free parameter will have name S, and so we have S2 and S3. And this then becomes the family, 2-parameter family of fitting functions. Let's put this into a matrix vector format. AU equals V. Here are the equations. Here are the unknowns. Generate matrix. Matrix is A. Right-hand side vector is V. LeastSquares applied to A, V. Free parameter will have name S. You get this vector. So now the null space is 2-dimensional, and you have an arbitrary member of that null space added to a particular solution. And this is the code that I use to take this information that's in this vector and put it into the fitting function. The way that works is, here is the vector ABC, and this vector V is this vector here. You need A equals this, B equals this, C equals this, and equate will do that. It will set up a list of equations of that form, and then evaluate f of x using those 3 equations, and here's your fitting function. So these 2 things agree. Let's get the minimum norm solution. So you include optimize equals true, you get the minimum norm solution. And I'm going to check that if I project the general solution, that's this vector, onto the row space, I get the minimum norm solution. So I showed this before. Row space, transpose those basis vectors, you form a projection matrix. So this is the projection matrix. This is the projection of the general solution onto the row space, and that's the minimum norm solution. So again, in too few equations, suppose the model is nonlinear. Could be consistent or inconsistent. Here's a consistent example. So we need a nonlinear fitting function that's nonlinear in the parameters. I chose this thing. 3 parameters, A, B, C. 2 data points. And I will generate consistent equations. Define the fitting function. I'm trying to solve equations. F of 1 is 3, f of 3 is 1. I can solve for 2 of the parameters in terms of the third. I'm solving equations. If you have a tool and you have an amenable model that solve works, you can get a solution in the 2 parameters in terms of the third. This is what I got back in Maple. B is a function of A, C is a function of A, and this is then the fitting function that you get. The 1 parameter family of fitting functions. Now, if you tackle this as a LeastSquares problem, so here we have the 2 residuals squared added together, so this is the sum of squares. This is what that would look like. We find the normal equations, so you differentiate with respect to A, B, and C, and you do an LSSolve. You get back 1 solution. This is the member of the general solution that you would have found if you cannot solve exactly for 2 parameters in terms of the third. Let's draw some graphs. This is the parameter A. You see how varied that family is. So there is a value of that parameter that gives you this fitting function. But if you're working numerically, because you cannot or do not have the because the model can't be so solved, or you don't have the tools to solve it, okay, you would work numerically. You'd get this solution or a solution like this. What does that mean with respect to the fitting problem that you're trying to solve? So it's a question of what tools do you have, and it's also a question of how bad is this model? How entangled are the parameters in this model? And if you have too few equations in a nonlinear case and the equations are inconsistent, take a look at what happens. So we use the same fitting function, and we'll change the data points so that the equations, the 2 equations we're going to get, will come out to be inconsistent. At x equals 1, we'll have value 3, and we'll also have value 5. So these 2 equations aren't going to be necessarily inconsistent. So we define the function, sum of squares. So here, residual squared, added together. In this case, if we write the normal equations, derivative with respect to A, B, and C, we can hit it with Maple's solve command, and it does find C in terms of A and B. If you can't do that, you are not going to get a general solution. I've taken this solution and I've evaluated the sum of squares at that solution. That's the value of the sum of squares. This is the family, 2-parameter family, A and B out of 2 parameters, 2-parameter family of fitting functions. If you tackle that as a least squares problem here numerically. So now you've got the normal equations, and you say FSolve. So you're going to get a numeric solution. So you get this one numeric solution, and this is the one member of the fitting function family that corresponds. If you draw the graph, you have two parameters. There are parameter values that will give you this one function. But you got to ask yourself, what is the meaning of that one function? It's one member of a host of possibilities. What does that mean with respect to the fitting that you're trying to do? So again, it's an issue of how complex is the model and how strong are your tools. If you can't get one parameter in terms of the other two parameters, you're not going to get the full family. And if you don't have the full family, what are you really getting when you get one numeric solution? We move now to multivariate examples. Let's begin with too many equations, linear, and we'll do inconsistent. So we have a fitting function in two variables, x and y, and there are three parameters, a, b, c. And I need data points, so I have 9 data points, the direct product of 1, 2, 3 with 1, 2, 3. So in order to set this problem up, I said, okay, let's start with the values 3, 4, and 5, right? A, B, and C, 3, 4, and 5. Let that be the function little f. See, my fitting function is big F. And let's generate data from this function on that grid of points. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And we get these numbers. Think of them as the z values. Then I just rounded them, made them integers, and that kind of puts some noise into the problem. And this is my matrix A, this is the vector V. Let's do a statistics linear fit, because statistics is where you would have to go for multivariate problems. These are the basis functions. 1, 2, 3 basis functions. Data is contained in A and V. The unknown, the independent variables are x and y. And Maple comes back with this fitting function. So this is what I call phi fitting function. So little f is what I started with. And I graph the two. The red surface is the fitting function, and the green surface is what I started with. I seem to have gotten a pretty close fit. If you go here to the linear algebra package, turns out you can use that because it's a linear model. Fitting function, capital F. Make matrix from equations. So this is the x value at a point. This is the y value. And these are the right-hand sides, or z values. And so you get equations, and then we have a matrix, I call it C, and a vector of unknowns, I call it U. Well, That's the vector v. In this language, we'll call it c and u. So least squares, cu, get three numbers representing a, b, and c. Remember, this was supposed to be 3, this was supposed to be 4, this was supposed to be 5. Close. I put these numbers into F, and I use that same trick I showed you before. Use the equate command. This creates equations, a equals b equals c equals, and then you can use the eval command to evaluate this general function using that information in those three equations, and you get this fitting function here, and compare that to phi that we got from the statistics package, and you see that they're the same. Multivariate least squares, again, too many equations, nonlinear. And that will necessarily mean you have inconsistent equations. So here's an example of that. So remember, we have to construct a model, an example, and I'm going to load the linear algebra package. Here is a function, nonlinear. I need some data. So I have this matrix, x, y, f of x and y. So I generated these data points, x and y, and used this to give me some idea of z values. So let's tackle the solution of this problem. We'll begin by initializing. So here is the fitting function, and this is the sum of squares. So m sub k1, m sub k2, these are the x and y values. This is the function at that point. This is the supposed z value. These are the differences, so these are the residuals, sum of squares, add sum of squares. And there are 5 such data points. What does the statistics package provide for this problem? There's a nonlinear fit command because this is a nonlinear problem. This is the fitting function. Fitting function. M, the matrix M, contains all of the data. X and Y are the independent variables. And in this case, I'm going to ask for the fitting function and the residual sum of squares. So this is the fitting function, and this is the residual sum of squares. I drew a graph. You can see the data points and the fitting function, and the data points seem to lie on the fitting function. And I think if I were to remove the lighting, you wouldn't get that glare up in this corner. You can see that the fitting function does a pretty good job of capturing those data points. And let's see what happens if we tackle this through the optimization package. So in the optimization package, we have the LeastSquares or LSSolve command. The input is a sequence of residuals, function value, z value. The return is half the sum of squares and values for a, b, and c. So here I've doubled the sum of squares, 0.09, and I compare that to what happens if I use the minimize command. So I'm minimizing the sum of squares, and here you get full value of the sum of squares at this optimum point. Remember, it's a local optimum, A, B, and C, and they compare well with the values up here, and compare that to the values up here. Right? A, B, B, C, C. Now we'll look at some cases where you have too few equations. Let's do a linear model, and let's jump right into the inconsistent case. So again, let's install the linear algebra package and create a problem. So we need a matrix and a vector. Matrix, vector. Now this matrix has rank 3. So the model will have inconsistent equations. Linear fitting function, 3 variables, 3 independent variables, x, y, z, and 4 coefficients, c0, c1, 2, and 3. So that's the setup of the problem. And now let's see what techniques, tools Maple has for solving it. So the tools available here live in either the linear algebra package or the statistics package. Well, let's see what's in the linear algebra package. So first thing we do is we form an augmented matrix, AV, and reduce it to row echelon form to verify that this is an inconsistent system. This last equation is the equation 0 equals 1. The equations are inconsistent. General solution. So LeastSquares, AV, name of the free parameter is S, and it's got a 4 subscripted. So the null space has dimension 1, and you're adding to a particular solution a multiple of the basis for the null space. You can get a minimum norm solution here. LeastSquares, we put optimize. You get this minimum norm solution, and I floated it to make it a little bit easier to read. Let's project the general solution onto the row space. We've done this now twice already. This is the third time. So bases of the row space, make the basis vectors column vectors so that the projection matrix command can work. Project the general solution onto the row space. You get this minimum norm solution, and here I floated it and more easily seen to be the same. Now, if you working numerically so that A contain only floats and V contained only floats, then in this example the LeastSquares command would return the minimum norm solution. You can see that's what we have gotten back. Okay, so you don't get the general solution. You're working with floats, so you don't get the general solution, but we did get the minimum norm solution. So let's see what happens if we work in the statistics package. Well, this is a linear model, so we can use LinearFit. You give it the basis functions. Now, the basis functions were chosen to be x, y, z. They could have been functions of x, y, z, each one of those. But I kept this thing simple just to see what would happen. And I'm given the data as floats. These are the unknowns because there was a 1 I have to put a dummy name here, U. Maple detects it's not full rank. It does return the fitting function, which corresponds to the minimum norm solution. Now, whether that will always happen or not, I don't know. And I don't know how to tell. Now, it's time to talk about this SVD tolerance parameter. And what's going on here is that Maple prefers to use a QR decomposition to do the LeastSquares fit. Now, QR can sometimes fail on an ill-conditioned problem, in which case you would have been better off using singular value decomposition, SVD. And to detect if the problem is ill-conditioned enough to switch over to SVD, there is this SVD tolerance parameter. Maple does not default to SVD because that's more expensive computationally than QR. So Maple needs an estimate of the condition number. It looks at the singular values. Just computing the singular values is a little bit cheaper than getting the singular value decomposition entirely. So Maple looks at the singular values, and it returns them largest to smallest. So S1 is the largest and S4 is the smallest. And for some reason or other, it looks at the reciprocal. It puts the smallest over the biggest. So this is now an estimate of the condition number reciprocal. For this problem, that number is 10 to the minus 18. The SVD tolerance is 10 to the minus 11. This number is smaller than this number. The problem is more ill-conditioned than QR can handle. So Maple switches to SVD in this calculation. So you can see here it has printed out all of this information that we've seen before. Here is the model that it comes up with. If we move the SVD tolerance so that we stay within the realm of QR, then this is the fitting function that will get returned. And it's absurd. 10 to the 14, 10 to the 14, 10 to the 12. This is absurd. Okay? So it is important that the SVD tolerance be set appropriately for a particular problem. It was okay for this problem. If it gets reset to something that's not okay for this problem, you'll get absurd values. So if you have a problem and you get these absurd values, then that's a warning that you need to shift this tolerance level so that instead of QR being used, SVD is being used. So again, down here, too few equations. Nonlinear this time. And we'll try consistent. So the fitting function is the one we used before, and we need some data. So this is an x, a y, and an f of x and y. Made up this data so that we would have an example to work on. The data will give us a set of two equations and three unknowns, right? A, B, C. It's essentially an interpolation problem. You're solving equations. The matrix has rank 2, so it's full rank. And there's going to be one free parameter. In a nonlinear case, there's no theory for generating anything like a minimum norm solution. So this is definitely new territory. Well, by way of solution, let's see what we can accomplish. It's equation solving. So here is the function. Here are the two equations. The function evaluated at the x, the y, and this is the z. Do that twice, you have two equations and three unknowns. If the problem is amenable and you have strong enough tools, you can solve for two of the parameters in terms of the third. So I'm solving for b and c in terms of a. So here's the b, here's the c in terms of a, and you put that information back into the function. That's what the eval command does, and you have a fitting function, which is a one parameter family. Here's a here, a here, a here, and again, how varied is that family? So I have a slider controlling value of a for some range of a, and you get a sense of how varied the fitting function can be. If you use the minimize command, the optimization package, this is the sum of squares, right? This is a residual squared plus a residual squared. Hit it with minimize. You get an a, b, and c value. How does that compare to what we had here? Here, the b and c are functions of a, but here you get an a value, a b value, a c value. So you get this one fitting function. It's graphed in red. As we vary a, you see that the family includes this member, but again you have that issue. If you can't get the general solution because the problem is intractable or you don't have strong enough tools, you will get a single member of the family, but you have no idea what that single member is. You can't even rely on minimum norm because there is no norm. What are we talking about here, norm? And as a final example, let's look here. Too few equations, nonlinear, inconsistent. So what happens if your equations are inconsistent? Same fitting function, and I have made the data points so that the equations will come out to be inconsistent. Now, how do I do that, right? The x and y's are the same. The z values are different. So inconsistent equations are going to result. Here is the fitting function. One point, the second point. Sum of squares of residuals. The fitting function evaluated at the x and the y. Subtract the z value and square. This is the fitting function. This is the x and the y. And this is the z value. Difference, residual, squared, sum of squares. If you can get an exact solution to the normal equations, which is what I've got here, differentiate the sum of squares with respect to those three parameters a, b, and c, because we want to do a minimization or an optimization. Maple is able to come up with c as a function of a and b, giving a fitting function that is essentially a family of fits, two-parameter family. How varied is this two-parameter family? Well, by using the the same devices, we can control A and B. The family is quite varied. So what happens if you work in, numerically? Let's say you work in optimization and you minimize the sum of squares. You're going to be working numerically. You're going to get value of A, B, and C, one set of values numerically computed. So you will come back with one function. It'll be one member of the general family. Can you adjust A and B? Oh, you can see that you could probably adjust A and B to show that that one solution is a member of the family. Okay. Oh, we could always look up the values here. What are the values of A and B? A 0.8. Should we make that small? Yeah, it's getting better if we go down here. Okay, so you can see that working with a numeric tool, you will get one member of a general family. If you have no way of knowing what the general family looks like, what do you know at that point about the solution that you're trying to determine? I think we're running out of time, so I think I'd best stop there and see if there are any questions. Before we do that, let me just point out this is my email address. If you want these files, send me an email. There's my email address. Ask for the files, and I'll send you a download link from which you can pull the files. So let's see if there are any questions.